Alright, I know that was kind of a weird place to break the recording, but my computer started to auto-save at that point, and it was going to take it a while, so I just ended the recording, and we're now ready to pick it up again. We are not quite through with this problem yet. While we have managed to get the derivative completed, we still haven't actually solved for dy over dx. We are trying to find the derivative. So now you have to do a little bit of algebra to isolate your dy over dx. And to do that first, though, I'm going to rewrite this so it's a little cleaner and neater and easier for you to follow. I actually have here 2y times dy over dx plus the 3x squared plus 3y squared times dy over dx equals 0. Your goal is to isolate dy over dx. So this is back to algebra 1. If you want to solve for a certain thing, you get all of those items on one side of the equal sign, anything that does not have dy over dx on the other side. So I'm going to simply move the 3x squared to the right-hand side, and I'm going to leave the two terms with dy over dx in them over here on the left. Now, your goal is to solve for dy dx, so you need to get it separated away from those other terms. Well, since it's over here on one side all by itself, you can simply just pull out dy over dx as a common factor and isolate it. So I'm going to pull the dy over dx out front, which will leave me with 2y plus 3y squared equals the negative 3x squared. Last but not least, I want to get dy over dx alone, so I'm simply going to divide this quantity over to the other side, and I will have ended up with negative 3x squared over 2y plus 3y squared. You can now see that you've isolated dy over dx. Now, since this is a fraction, you do need to do one last algebra check. You need to look at the fraction and go, is there a common term I could take out of every single term in that whole fraction? There's not a 3 in common to all three terms. There's not an x in common to all three. There's not a y in common to all three. So no, this one cannot be reduced. This would be your solution for your derivative. Now, going back to what we know derivatives represent. Derivatives represent the slope of a line tangent to a curve at a given point. So you could right here, if they said find the actual slope, if you knew the actual coordinate, this time you would have to know both an x and a y coordinate, you could sub in a coordinate, a number for x and a number for y, and calculate slope. You can still find slope even using this formula. Now in our next problem, we will actually go ahead then and find the equation of the tangent line once we get done. We're going to try another one that's similar to this. It's got a little more pizzazz in it. We want to find dy over dx again. Now I know some of you thought this notation was pretty useless and why do you care about writing this weird dy over dx? But in reality, it has lots of helpful uses. When it says find dy over dx, it's saying find the derivative of y, but do it in terms of x. X is what you call what I think of as the normal variable. It's the one you don't have to do anything special to. We normally want to do the derivative of x. We wish we had y equals a whole bunch of x's. Since we don't, we're going to treat it like our normal variable. And however, anytime we do the derivative of y, we have to do it and think, oh, it's like a chain rule, because y actually represents some quantity in terms of x. We just don't know what. Now, you'll notice this first term presents us with an extra challenge. This first term has x squared times y cubed. You have multiplication happening there. So in order to do this derivative, you will have to do a product rule. Now, personally, I usually take the coefficient out front and attach it to the first variable, like I did here. I put the 3 with the x squared, and then I do the y cubed. So we actually have to do product rule here to find this derivative. So we're going to start out with first. The second would be no big deal, 3y squared. But because it's a y, I'm saying, oh, I would chain rule that if I knew what y was in terms of x, and I'm going to add on a dy over dx. I would do the derivative of the inside if I knew what it was. Okay, now, have I completed the product rule? Answer would be no. I've done first, the second. So now I have to do plus second. I am not doing the derivative of this y, so I do not put a dy over dx on it, times the derivative of the first, and since that's an x, it's just a plain old 6x. Okay, moving on to the next term, 4y to the fifth. That's an easy 20y to the fourth, but it's a y, so we will tack a dy over dx with it. And yes, you can even do trig functions with this. Derivative of sine we know to be cosine, so this would be 6 cosine y, but because it's a y, we'll put a dy over dx on it. And then last but not least, ax to the fifth becomes 40x to the fourth. That's not a y, so we are not going to put a dy over dx with it. Now, here's where I have more people mess up these problems, particularly these ones that had product rules in them. You need to take one extra line of paper and go back and clean this up before you try to actually isolate dy over dx. These first two terms here, this is all multiplication. They need to get multiplied together. So we need to say that that's really 9x squared y squared times dy over dx. This next term could be in a better order. That would be better as 6xy cubed plus 20y to the fourth dy over dx, and the rest of these are okay as they're written. So we just need to recopy them. Okay. Now you can start trying to isolate dy over dx. Since I know I'm going to put all the dy over dx's on one side, and it doesn't matter which side, in this case, since I've already got two of them on the left, I'm going to keep them on the left. I know I'm going to pull dy over dx out, so you can actually save yourself a line of paper here, pull the dy over dx out right now, and just write down the terms that you would have with the dy over dx. So I'd have 9x squared y squared plus 20y to the fourth minus 6 cosine y. I'm bringing the 6 cosine over from the other side. On the right-hand side, I would have had to bring over the 6xy cubed, so it's now negative, and add the 40x to the fourth. Last but not least, I can now isolate dy over dx and divide this monster mess here to the bottom of this thing. Don't know why we thought that should be negative. And I would have this lovely expression. Are you done? Well, you need to stop and check. Is there a common factor to every one of them that we can reduce the entire fraction? Looks like 2 is in common to most of the terms, but unfortunately you can't take 2 out of 9, so you can't reduce it there. 3 is in common to some of them, but not all of them, so we can't take it out. They don't all have an x, and they don't all have a y, so there are no common factors. We can reduce it, and so there is our successful derivative. Now, I want to take this one step farther, though, and show you that you really can find the equation of a tangent line using this process. They might say, find the equation of the tangent line at the point 1, 0. Okay. Since you know it's 1, 0, you can go back in here and find the slope of your tangent line by simply filling in 1 for every x and 0 for every y. And if I do that, I'm going to have negative 6x times 0 cubed plus 40 times 1 to the fourth. We have 9 times 1 times 0 squared plus 20 times 0 to the fourth minus 6 times the cosine of 0, and we all know the cosine of 0 is 1. Okay, I believe this will simplify pretty nicely. Anything times 0 is gone, so that term's gone, that term's gone, that term's gone, because those all get multiplied by 0. And I believe I would be left with 40 over negative 6, which we could then reduce down to negative 20/3. So ta-da, you got a slope. They want the equation of the tangent line, so you can come up here and go, okay, point slope land. I have my coordinates because I got 1, 0, I got a point, I got a slope. So y minus my y coordinate of 0 equals my slope of negative 20/3 times x minus my x coordinate, which is 1. And in that case, then, I'm going to end up with negative 20/3 x plus 20/3. And there would be the equation of my tangent line. So you can still find the equations of tangent lines, even with these very messy expressions. We're going to stop right there and record one last part.